Decision trees for classification in Python. By the end of this course, you'll understand what a decision tree is and how it functions, when decision trees are the right tool to use and when they might fall short, how to build, visualize, and optimize a decision tree for classification tasks, practical techniques for pruning trees to avoid overfitting. So, what is a decision tree? A decision tree is a supervised machine learning algorithm used to make predictions. Classification trees predict class assignment when the dependent or output feature is categorical. Regression trees predict numeric outcome variables. And note that the term CART is an abbreviation for classification and regression trees and was introduced by Leo Bremen. When to use decision trees for classification? When you need interpretability, when you need to know what features are best at splitting the data into the separate classes. And this is a good algorithm when you have small to medium-sized data sets or when you require a quick model with minimal processing. Another bonus for decision trees is that they can handle mixed data types, nonlinear relationships, outliers, and missing values. Some use cases in medicine is to predict patient readmissions based on their medical history and treatment. In finance, you can predict the likelihood of a customer defaulting on a loan based on their credit history. Education, we can predict whether a student will pass or fail an exam based on hours of study and previous test scores. In business, we can predict if a customer is in danger of churning based on their engagement with a product or service. So how exactly do the decision trees work? It works by splitting the data into smaller groups based on features that best separate classes in classification or predict values in regression. The decision tree starts with a root node that represents the entire data set. At each node, the algorithm decides which feature to use for the split by evaluating various features and selecting the one that best separates the data. The structure of the decision tree, it begins at the root node, which is our starting point that represents the entire data set. And then it has branches, which are the connections between the nodes that represent feature-based splits. Internal nodes are the points where data is further split based on features. Leaves are our terminal nodes, and these endpoints that represent a final class or prediction. Pure nodes are those nodes that contain data from only one class. When selecting the best feature to split the data, we can use metrics like the Gini impurity, entropy/information gain. These are the most commonly used. Gini impurity measures the impurity or mix of classes within the node, aiming to reduce the chance of incorrect classification. Lower Gini values indicate better splits. Entropy measures the level of disorder or impurity in a group ranging from 0, which is pure, to 1, which is mixed. Lower entropy means better purity. And information gain calculates how much purity is gained from the split. The higher the information gain, the more effective the split. We use Gini impurity when you need something simple and fast metric for splitting the data and is less computationally expensive. Entropy is more theoretically sound and relates to the concept of information gain and provides a clear mathematical interpretation of the uncertainty in the data. Log loss is something that's not quite as commonly used, but we use it when you need a probabilistic output rather than just the class predictions. Log loss evaluates the accuracy of the predicted probabilities, penalizing incorrect predictions based on confidence levels. Here's a summary. We use the Gini impurity when you have large data sets that require binary splits for classification tasks. Entropy is best when you have non-binary splits, data sets with complex class distributions. And again, log loss, which is less commonly used, but it's when you want to know what the probabilities are for a class assignment. Okay, let's take a look at this example. Here's a data frame where it is data of used car information. And the decision or class is purchase, whether or not to purchase this used car based on these features of year, the make, the price, number of owners, if it's personally used, the type of vehicle or the body of the vehicle, is a pickup, a sedan, mileage, and if there's any damage. And so the class is yes or no for purchase. And this is our root node. This is where we're going to start. This represents the total data set. Here, the feature that we're splitting on is the number of owners being less than 2. And so here our number of owners is just one owner. And what happens when we split on the situation is, hey, it's true, we have less than 2 owners here. what happens to the purchase column is that they're all no, don't purchase the vehicle. So here we have no's here. We don't have any split in the purchase. We don't have any yeses in here. And so because they're all the same class of no, do not purchase, this is a terminal node. So this is a leaf, this is a leaf. We can't split it any further. This is an internal node because the purchase has no, yes, 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 no in it. And so we can split it further. The next feature that we use is mileage being less than 100,000 miles. Here, when it says less than 100,000 miles, we come over here and says, oh, yep. And the purchase is yes. And they're all yeses, and we can't split this one any further. And so now this is a leaf. And this one could be split again. But there's a danger in just splitting until you get all the way down to these pure nodes, because you can cause your model to overfit and not generalize well to new data. And we'll talk about some ways to kind of reduce those issues. So let's talk about the pros and cons of having or using decision trees for classification. The advantages of decision trees is that they're intuitive and easy to interpret. They can handle both categorical and numerical data, and they are ideal when interpretability is important. The disadvantages of decision trees is that they have a tendency to overfit to the training data, and they have high variations in results. And so it makes their predictions really unstable. They are, however, powerful in ensemble methods such as random forests or gradient boosting, where multiple trees work together to mitigate these weaknesses. You can improve your model performance using cross-validation. And the method is to split your data set into training and validation sets multiple times and training the tree with different parameters. In this situation, we're talking about max depth, but it could be minimal samples, and for each leaf. And we're going to use some of those different parameters when we actually perform the analysis using Python. The goal here is to identify the depth that minimizes the validation error when we're using max depth. And we do this because it helps prevent overfitting when the tree is too deep or underfitting when the tree is too shallow. We monitor the tree performance using the training and the validation accuracy. If the training accuracy is high but validation accuracy is low, your tree may be overfitting, suggesting you need to reduce the max depth. And also we need to look out for accuracy plateau. If increasing depth does not significantly improve the validation accuracy, there's no need to go deeper. And that's true of max depth or any other parameter that you would like to use. Here we are at scikit-learn looking at the decision tree classifier. And here we have the parameters, the criterion. We talked about Gini and entropy, log loss, and it gives you information about them. The splitter, whether you want to choose best or random. The default is best. The criterion for the split on the feature, the default is Gini. And for maximum depth, the max depth of the tree, if you have none here, they'll be expanded until all the leaves are pure. And so this is going to cause an overfit for sure. Minimum sample split. This is the minimum number of samples required to split an internal node. Minimum samples leaf. The minimum number of samples required to be at a leaf node. And so there are other parameters that you can use to help try to improve the model fit for your decision tree. If you want to get access to additional resources like the decision tree classification notes that go a little bit more in depth than what we have done here today, you can definitely get this from the GitHub. It's at Enhance Impact Decision Trees, and I'll create a link and that will be in the description. We have a decision tree classifier notebook, the decision tree classifier Python script, as well as the usecars.csv file that we're going to use to run the analysis. To perform the analysis, we're going to actually use Google Colab. And we're using Google Colab because you don't have to download anything. You can essentially work on this data anywhere. If you're at the library, or if you're at home and you don't have space on your computer to download Anaconda or Miniconda, then you can just use Google Colab here. And just also for ease, so we don't have to spin up an environment and worry about version control and packages and whatnot. So here we're going to import our libraries and load the data. The matplotlib.plyplot is going to allow us to see visualization. Here is going to allow us to, the decision tree classifier is going to allow us to actually create the model. We're going to split our data into training and test sets or validation. And we have an accuracy score. The accuracy score that we're going to use, that metric, will be the percentage correct. Just the percentage correct. You have other things you can look at, like the percentage of, precision recall, F1 score, and different things you can do with accuracy score, but we're going to focus just on how much of it is correct. And we have sklearn.preprocessing. We need this one-hot encoder to numerically encode the categorical features. So convert those categories like the make of the car to ones and zeros. We're going to read our data set in with pandas. And so here, our data set is over here, use cars.csv. You can upload your file. And I forgot to show that to you here. Let me go back to GitHub. If you want to download any of these resources or just clone the repository, you can come here. All right, so let's run this one. Here we're going to view the first 5 rows of the data. And this provides us with the year, the make, model, price, number of owners, of what the car was used, how the car was used, whether it was multiple user or personal usage, the body type, pickup, SUV, mileage, damage, accident, and whether or not to purchase the car. What you'll notice here is that I decided to remove some of the columns, like model, because there's too much variation in it. It's not going to be useful for a good split. And I also decided to remove accident, because if there's an accident, there will be damage. And sometimes if there's a damage, there may not have been an accident. And this is the one that's going to give us more information. So we're going to remove accidents so we don't have any redundancy or correlation. And so that's what we're going to do with that. The information, this right here, this code, data.info. That data.info is going to give us a description of the data set. How many columns? We have 93 rows, or 93 records, ranging from 0 to 92. Because we start off with 0 instead of 1 with Python. They tell us for our columns if we have any missing information. So here, no missing information is complete. They tell us the data type, year is integer, and the ones that say object, those are the categorical columns or features. The categorical columns we're going to convert to ones and zeros. I sometimes even expand the columns based on how many levels it has. So for the column of damage and purchase, since they're already in yes, no format, I'm just going to map no to 0 and yes to 1 for damage and purchase columns. For the other columns, the way we're going to treat these other categorical columns is that we're going to use one-hot encoding. And we'll use one-hot encoding on the make and what the usage, as well as the body. So this is the part where we take our data and we're going to subset or filter our data to those specific columns that we want, because we want to drop a couple of them. We're just going to keep the ones that are of interest. Our binary columns, the ones that already have yes and no, the purchase and damage, we're going to go ahead and map them here. So using a for loop, we're going to map these to no for 0 and yes. 0 for those that are no and 1 for those that say yes. Now we're going to separate our features and target. So our feature columns which are going to be our input features. We'll have everything except for purchase, and then the purchase will be off to itself as our target column. We'll define our categorical columns. We have make, use, and body as the remaining categorical columns that need the one-hot encoding. And then we have our numeric columns, which are year, price, number of owners, and mileage. Here we're going to instantiate the encoder. That's our one-hot encoder, and perform the transformation on those categorical columns for the X on the X data frame. Once the encoding has occurred, we'll then encode the data frame with the new feature names and create the data frame here, pd.data frame on this encoded information. Now, once that has occurred, it's time to put all of the data frame right back together with the numerical columns, the encoded data frame, and the binary columns. And what you'll notice here for this binary calls 1, we don't want all of the binary columns as part of the input data frame, the input features, because here the binary columns include purchase, which is our output feature, or our target feature, and the damage. And so all we want is this right here. We don't want binary. We don't want purchase as well. So for the binary columns, we're going to select damage here, and so we're going to use an index. This is position 0. This is position 1. So when you come down here, this is binary columns position 1 for damage, and we made that a list so we can put those all together. And so what it looks like We're going to take a look at the first 5 rows of that. And here we are. So we have the year, the price, number of owners, mileage. Damages are in ones and zeros. And then you see that additional columns were created for Audi, for BMW, for Buick, and Cadillac. And we have some repetition with this make BMW, but it does not impact the analysis. Here for this .loc, this is a warning. We don't have to worry about the warning. It just says that they prefer that you use a .loc for indexing, and it's okay, no problem. All right, so we're going to train our decision tree with the varying max depth, and what we're going to do here is we're going to test this model out. We're going to create a bunch of models with different depths so that we can see which depth is the best for creating this model. That's right, for creating this model. So here we split our data into training and test sets here. X train, X test, Y train, Y test. So this is our train test split. So we have X final, Y, and then we have our test underscore size. So our test size is going to be 30%. So we have 30% of the data, and the random state is equal to 42. This is us we call it setting the seed. So the random state will allow us, if we use this 42, it allows us to come back and get the same results every time because we use random state 42. And so it's useful for reproducibility of results. So having a random state is good. Remember, the test size is 30%. So what we're going to be training the data on is 70%. And if you remember from going up here, that the data has 93 entries. And we're going to use 70% of 93 in order to train the model. So here they tell us 30% will be for testing, 70% will be for training. So if we take 70% or 93 times 70%, that's 65. Okay, so we'll be training the data on 65 records. We were going to store the accuracies for the training and the testing, so 65 are here, and the remaining will be for testing accuracies. And so these are our empty containers that we're going to store our accuracies in. Convert the columns names to strings. This is what's happening here for training and for test. And now this is the part where we're going to say what the different depths will be that we're going to train the models on to see which is the best depth. Here we have a depth of just 1 up to 20 different levels for the tree. So for depths, it's our for loop, and for this for loop is just saying, hey, create a decision tree classifier with the depth. Do it the first time, it'll be max depth of 1, and then it's going to run it. And then we get an accuracy for the training, you get accuracy for the test. And they'll do it, up until 20 times the same thing. And it'll be plotted. So when we come here, it says predict on both we're going to fit the model, X train, Y train. This is the model. And then we're going to make the predictions on the training data based off of this model. Then we'll make the predictions of whether this is going to be a purchased vehicle or not, yes or no, on the testing data based off of the model that was created here. Then we're going to append these training accuracies to the train accuracy and test accuracy lists up above. And so here we have accuracy underscore score, Y train period. Y train is the original purchase result of whether or not the car or the automobile was purchased, yes or no's. And this is the predicted value from the training. It's a prediction here. This is the actual Y underscore test for the test data. And this is the predicted value. And so here we're going to plot the data, 8x6 plot, and the label is going to have the training accuracy or testing accuracy here. And then these are the different depths, 1 through 21, or 1 through 20 actually. And then we have our training accuracy and test accuracy. Here are our labels. Max depth accuracy is the Y label, and the title is accuracy versus max depth for decision tree. We're going to have a legend, and there will be a grid, and we're going to show the graph. So here, let's make sure we're ready to run it. Go ahead and just run that. I'm using Shift Enter to run it. And here you go. And so here's our image. Here's our training accuracies in blue, the testing accuracies in orange. And you can see where the plateau happens that we talked about before. That's when there is no more improvement. It just levels off. Here it's 100%, so you know it's overfit. If you use anything past 6, it's going to be overfit. The comparison between the training and testing, you can see here is the widest gap here. This is also a pretty significant gap. And this is where they get close. This is the closest spot. And it's also the place where the testing accuracy is the highest, and it begins to drop off, and then there's a plateau. So adding any more depth to the tree past 5 just is not really going to give any better accuracy of the model for testing new data. Here we're going to actually print or plot out the decision tree using GraphViz. So from sklearn.tree, import GraphViz, and we're going to have a confusion matrix, which is going to show us our true positive, false positive, true negative, and false negative accounts for the data. So let's do that. And so now we're going to initialize the model with the best max depth. And our max depth, again, remember, was 5. And in this situation, we also included some minimum sample split of 6 and the minimum samples leaf of 10. And that's from actually doing some additional work and saying which, just testing out which of these other parameters would be better for this data. So we're going to have our GraphViz and all these other things here. So now here's our tree. And our tree is color coded. This is one thing I do like about the tree, is that it's color coded. And what we have here is that it tells us the class. So the class is the purchase class. So if it's a 0, that's a no. If it's a 1, it's a yes. So we're going to purchase the vehicle here. It says nope, don't purchase. Don't purchase. And what that means is that the most of these in our data at the root node are vehicles that were not purchased. So 37 out of the 65 samples here was not purchased. This is 65. I'm trying to get to that. Yeah, 65. So 65 out of the 65, 37, more of them were not purchased, and 28 were purchased. The Gini impurity tells us it's about 0.49 just for that entire data set. So it's a mix. It's not down to, completely 0, almost at the halfway point. Almost like that's a close split. The first decision rule is whether or not there's damage. So 1 says that there is damage, 0 says that there's no damage. So is it less than 1, meaning no damage? Yes. If it's no damage, then the class is to purchase. This is okay because 28 out of the 46 is more than 18 out of the 46. That's why this node is assigned a class of 1. The Gini impurity says it's 0.476, so it's a little bit more pure or more pointing to a specific class here than even up here, because this is 0.49. On this split, it says, you know what? This is actually false. It's not less than 1. In other words, it is equal to 1. And that means that there was damage. And so here, this class is 0. Do not purchase the car. So you have 19 out of 0. And so since there are no instances of the class of yes, purchase the car, this is a pure node. This is a terminal node, and it's a pure one because it's only one class assignment, which is 19, don't purchase. This internal node here can be split further. And so we split again. It says, hey, is the car has less than about 91,000 miles? Yes. Then yeah, it's another darker box here. It says, hey, yeah, you should purchase this vehicle. So 5 says don't purchase. 18 out of the 23 that's in this bucket, it says, yeah, you should purchase this. And the Gini impurity is higher. See, now it's 0.34, so it's getting closer to 0. And so this is how you work your way down the decision tree. Okay, this is how you interpret the decision tree. Also, you'll notice here on the side the decision tree PDF and the decision tree here. These are plots that are the artifacts of this work here. Here we export the DOT file for visualization, or the dot file for visualization. So export GraphViz. This is what happens here. And this is the best, so this is what we're working with. Okay. And they tell you different things about it. You notice the box, the edges are not just perfectly square, they're rounded. It tells you here, rounded is equal to true. He has some special characters. They want it filled. And so this is the stuff that we have in here. Okay. All right. All right, if you want to look at the accuracy looking at the confusion matrix, we can do that here. Okay. This is to predict on the test set. So here, Y test prediction. This is the test predictions. How well did the model perform on unseen data or new data? This is what this is doing. So we generate the confusion matrix. This is where we read it in from sklearn.metrics import confusion matrix display, so you can see it. And this is a display of the confusion matrix. Confusion matrix display. This is confusion matrix. And they're going to display the labels, CLF best.classes. That's how we get the class labels. And then this, they say, hey, we want them in blues. So I'm going to make it in blue color, shades of blue, with their title and then showing it. So the things that we're interested in is, hey, how much of this stuff is actually true? When things were true, how well did we predict that it would be true or false? So here, the true label is 1. So yes, purchase the vehicle. Okay, 8 times out of our sample, we said, yeah, predicted matched with what the actual value of the true label matched with. Hey, don't buy the car or truck or whatever it might be. It was 14 times. So here is a situation where, what I look at often, unless there is some sort of specific reason to be, you have to be extremely cautious. There are some instances where you have to be cautious, and you can't just look at the predictive accuracy. In cases like whether or not it's cancer diagnosis is an example. But here I'm just concerned about just straight up the accuracy. How accurate is it overall? And so 14 and 8, these boxes here, they weigh out a lot more than these other ones where you had false, where you had a mismatch between what was actual and what was predicted. So let's take a look again at this accuracy score. We're going to use the training and test accuracy. So we have best predict X trained, best predict X test. And so these are our prediction accuracies for both of these here. And we have our accuracy score. Okay. So here, we're going to look at our accuracy score between the two. All right. And when we look at this, what we're looking for are numbers that are not too wildly different. Here our training accuracy is at 0.83, which we'd expect it to be better than the test accuracy, but it shouldn't be way better than test accuracy. That's when you know you have something overfit. And if your test accuracy is kind of weird in a way where it's actually higher or too super close to than this one, then you might have some underfitting going on. All right, now this is the same method that we used above, except now we're going to do some testing of different parameters, like minimum sample split, minimum samples leave. Here we have different values that we're going to test out, different depths and ranges. And I'll include this code. It's already up on GitHub, and so you can include it and kind of work with it. But I'm just going to run it so that we can get what the accuracy is when the best of all of these are selected, when they're run together. The maximum depth, it says 8, minimum sample split is 10, and minimum samples leaf. That we should build the model using these. These are the best parameters. And sure enough, for the training accuracy, it's almost 100%. It's 98%. But look what happened to the testing accuracy. It's so much lower than the training accuracy that your model is likely to be overfit. It's similar to what we had before up here, where we have 79. But the fact that this is so much higher than what we saw before is that if you use this on new data, it's likely that it's not going to generalize as well. You might not get even as good a accuracy as what we have here. So yeah, this is it. That's the end of the tutorial here today, you guys. I hope that you enjoyed the video, and if you do, give it a thumbs up, like, subscribe. It's great motivation for me to continue to make the videos. Yeah, until next time, be well.